So once again, my name is Damon Tordini. I'm a simulation application specialist here at Talkridge Systems. And so basically, my main focus here is providing training classes, support, product demonstrations, pre-sales, all kinds of things, basically, just to further educate everyone on the capabilities of the various simulation tools we have for SOLIDWORks, the offerings that Talkridge System has. And in this case, what we're talking about specifically on the webinar today is what has been added to SOLIDWORks 2015 from a simulation standpoint, everything from improved capabilities, better performance, and what things we think are the most important that are going to help your everyday productivity. So we'll have a little introduction, and then I'm going to break down the enhancements that have been added to 2015 by the three main simulation products that we offer. SOLIDWORKS Simulation, which is our stress analysis product, Flow Simulation, which is our CFD or fluid analysis tool, and then finally SOLIDWORKS Plastics, which is for injection molding. I realize that not all of you will use all three of these products, but most likely I would assume you'll be using at least something from here, and maybe you'll get a little more information on the products that you don't use, and you might decide that it's something that would be beneficial for you. And of course, you'll have the ability to email me or your account manager at the end if you have any more questions. So first of all, just so you're aware that the general themes of the SOLIDWORKS 2015 release, what the developers were going for, is really similar to the themes that they've always believed in as far as SOLIDWORKS, which is that SOLIDWORKS should be used to improve your everyday productivity. And if the program can't help you do that, it's not really doing its job. So most of the enhancements that they put into the software, as you know, are user requested. And of course, if a user thinks that an enhancement or an improvement to the software is necessary, there's a good chance there's a lot of people out there that are going to agree that that particular enhancement will enhance their everyday productivity. So it's all about getting your work done faster, optimizing processes, and utilizing more tools that can reduce upfront costs in the whole design and operation process. So hopefully you'll see some of that philosophy in the enhancements that we're going to cover, the specific functionality. But other than that, I just want to point out that the enhancements that I'm going to showcase today in the simulation tools is not all of the new capabilities that have been added in 2015. These are sort of the highlights. This is the short, 30-minute abbreviated version, the best of, if you will. So if you're interested in learning about all of the changes and enhancements to 2015 for all of the different areas of the product, you can go in the SOLIDWORKS interface to Help and then What's New. And there will be either a PDF or HTML version of the full What's New document. It's pretty long. It's like 150 pages of enhancements. And you'll see some examples and descriptions of what the new capability does, why you would use it versus an old way of doing things, etc. So let's talk about SOLIDWORKS Simulation first, our stress analysis product. So first of all, if you've used SOLIDWORKS Simulation before, you're probably aware that when you do a stress analysis, there are different kinds of stress analysis you can run. A basic, static, or linear stress analysis, which is really useful for quickly analyzing larger assemblies for common loads like gravity or forces or pretty much any kind of static loading that you'd like. But then there's also more complicated loading scenarios like nonlinear analyses, where you might be checking for the post-yielding behavior of something. So one example of that is this cap insertion, where you might have like a plastic fitting that needs to be pressed inside the housing, and you want to see how the contact of the clip is going to behave, and perhaps what the insertion force required is, etc. So that would require a nonlinear analysis. So we can turn on our SOLIDWORKS Simulation add-in to run that kind of study, and in this case, we're going to use the 2D simplification here to make that analysis run a little bit faster. Now, even if you use the 2D simplification, though, you are probably aware that a nonlinear analysis takes quite a bit longer to run than other types of studies. And so one drawback to that, of course, is that if you wait all that time to run the analysis and then find out at the end when you go look at your results that you made a mistake, of course, that's wasted time. So if you want to make sure that you've set up the problem accurately and that the results are sort of in the ballpark that you're expecting, we now have the ability in simulation to view the results of your simulation during the nonlinear solve process. So you can see right here, for example, that I'm still currently solving this nonlinear 2D simplification study. Each of those time steps is currently being calculated. I'm at about 45% right now, but I'm able to see on screen the result plot, in this case the von Mises stress, being updated real time. So I already can be aware that, for example, I put my restraints in the correct position, I'm pushing down the cap in the correct direction, I've set up the contact properly, I could see the clip bending there, and so any set of conditions that I was unsure about, I'm immediately getting some feedback. And I know that I've set up the problem the right way, and I also know, of course, that the results are in the ballpark that I was expecting, and now that the full study's finished, of course, I can look at the other result plots, interrogate the model, figure out how I might want to make a design change, and all the other normal operations. But now with that live results viewing during the solve process, hopefully that'll save you some potentially wasted time the next time you do make a mistake like me and flip the direction on a force or something. Some other productivity enhancements as far as the stress analysis goes are some neat ways to quickly figure out, first of all, if certain load cases for an object are worse than others. You might be aware that if you have a product that is going to be loaded in multiple different scenarios, for example, one time it might be just a normal gravity load. In another scenario, someone might be pushing on it in a certain way or applying a torque, or different loading scenarios to describe different conditions that it's used in, the different scenarios that the product is supposed to operate in. Previously, you would have had to either create a separate study or potentially create a design study with multiple iterations or multiple scenarios to try to account for what would happen in those different loading scenarios, right? Now in 2015, there's a new load case manager that can help you do that more easily. So first of all, the load case manager is set up first by creating a study and applying all of the loading conditions that might be applicable in each of these situations. So here we've got a bracket basically for a mount arm here that has a downward load of about 2,000 pounds, a right load, gravity, torque, all of these things. And then what we can do is go into the load case manager interface here, which is brand new. And what we're able to do is create as many load cases as we want, simply by clicking here in this table and adding a new row. And within each load case, we have a simple checkbox where we can either turn on or leave on any of these restraints or fixtures or other conditions, or we can turn them off. So in this case, for example, the downward force is set to suppress, which means it won't be active. Or I could leave it on, but I could also change the value. So it's not necessary to create a brand new study just because you want to make the force half as large as it was in the previous run. So the benefit of this, of course, is that you can analyze multiple loading scenarios, multiple descriptions of what the loading that's going to be active is, multiple use cases, all at once, and you can even combine the different load cases to figure out, for example, if load case 1, which is downward and lateral together, is worse than the secondary load case 2, which in this example is a 20G vertical load plus that lateral load. So that's just a simple equation manager in this box here. So once it's done, of course, you can go in and view the results. We have this nice results view table here. And similar to design study, you can set up sensors which describe which results are important. And when you run the analysis, you'll see a nice table display here. Let me go ahead and run this one back in the first study here. And so similar to design study, it'll start to populate that table, and we'd be able to quickly figure out which of these loading cases or which combination of loading cases is in fact the worst, which one causes the most stress or has the highest displacement, etc. So it's a much better interface for checking multiple loading scenarios all at the same time to figure out which one is the worst and which one you really need to design the product around. Another potential enhancement that would be useful if you're looking to run other types of studies beyond just a stress analysis would be if you want to analyze your product for frequency response, potential dynamic loading conditions, but you want to just start out by running frequency study. So here we have a dynamic analysis. This is going to be a harmonic study that will run on the dispersive bracket just to figure out if it was vibrating at various frequencies, which of those frequencies would be the most problematic. So you may be aware that a frequency study will at least give you the first part of that information by telling you what the resonant frequencies or natural modes of the object are. Now in 2015, we also have a new way to create what we call a frequency response graph, which makes it much easier to figure out which of those frequencies is in fact the most problematic or is contributing the most to the motion. So we can run the frequency part of this analysis, and rather than just examining the result plots individually and looking at the animations, the plot will be able to show us a nice graph explaining which of the frequencies has the largest contribution to the mode. So for example, I can create my frequency response graph and show the effective mass participation factor, which is sort of like a percentage of how much of the motion in a particular direction is being caused by that frequency. And so now if I look at this plot, I can easily tell, for example, in this case, that in the z direction, in this example, which would be sort of side to side, the first mode there, which is at 436 hertz, that's the one that's contributing most to that direction of motion. And then you can see like the fourth mode, and to a lesser extent, the 11th mode is also contributing. If you're talking about the y direction, sort of the up and down motion there, the second mode is the most important, followed by the fifth mode and then the eighth mode. It's also possible to view those as a cumulative plot, which looks like this, and makes it a little bit easier to figure out at what modes the full total mass participation has sort of ramped up to the point where most of that vibration is sort of being accounted for. So this is an easy way to figure out which frequency range is important to analyze. Speaking of the dynamic results, like I said, we would be running a harmonic study in this particular example on the dispersive bracket. In a lot of cases, though, if you're running an analysis to figure out what frequency something would vibrate at, and if you're running the harmonic study in SOLIDWORKS Simulation Premium to find the stresses from that harmonic vibration, you probably also would want to know how long it could sustain that vibration until the product fails. Previously, we could run a fatigue study in SOLIDWORKS Simulation to estimate the number of cycles a product could withstand, but we would only we'd be limited to the kinds of studies we could use to represent one cycle or one event, basically a nonlinear or linear static stress analysis. Now in SOLIDWORKS 2015, if we want to run a fatigue study, we also have the ability to choose linear dynamic simulations from Simulation Premium as the event. So in this case, if I've run my harmonic study, I can choose which frequency I'm interested in and specify the number of cycles that I estimate the product will be vibrating at that particular frequency. And that simply gets added into the fatigue study as an event. So it will take the appropriate stress from that harmonic study that I already ran at that particular frequency level. And I can even combine multiple vibration events of different frequency points on the same harmonic curve. So I could simulate that this particular suspension arm was vibrating 100 times at 50 hertz, 1,000 times at 500 hertz, and 10,000 times at 10,000 hertz. So in other words, I could simulate more like a real-world physical test, even a shaker table test, and figure out the accumulated damage, similar to you've been able to do with fatigue study for other result plots before. The last enhancement I want to talk about in SOLIDWORKS Simulation are some capabilities we've added to when you want to use shell mesh. If you're not familiar, shell mesh, which is also referred to as shell elements in a technical standpoint, is a mesh type that's commonly used for thin geometry, things like sheet metal parts, because it's a much easier way to represent the geometry and get good results of your analysis without as much meshing or solve time. So one of the enhancements that we've made in 2015 related to shell mesh is in the setup work that's required to create all the shell definitions. If you're aware, if you wanted to create new shell element definitions on, for example, the faces of an existing body, in the past you would have had to right-click on each one of those bodies, choose Edit Definition, and enter in all the information. What's the thickness of the shell in the real world? What is the type of shell equation that you're using to calculate the stresses within the body, if it's a thin or thick shell, and the offset options. Now in 2015, you can use the new Shell Manager interface to essentially create or edit all of the shells in your simulation at the same time, which is going to be much less cumbersome and much easier to sort of review overall what the different shell options are and figure out what exactly you've specified for your design. So in the table interface down below, for example, I can click on any of these bodies. For example, here I've got surface body 27 or surface body 31. And each of these is showing me, again, the type of shell, in this case thin, the thickness and unit that I've entered in, a 5mm shell here, the material that I selected for that body, the offset direction, which I can also preview, by the way. And then, of course, it allows me to update or change any of these values. So if I decide, for example, that the base lateral shell over here on these faces is not 5mm, simply click that one box and change it. The real thing, as far as the increase in speed when you want to edit these shells, is that you can now group shell bodies together. And using the left column there, the groups column, you can see that I've got some already created. And of course, I can manage the groups and create new ones. And the point of the groups is that each one of these will have consistent thicknesses, materials, and shell type settings, so that if I update one shell, all the other shells in that group can be updated as well. So again, it's saving on clicks overall. If I decide that the thin shells here in the base lateral groups should be a larger thickness instead of 5, I can go in here, click on one of those. Here I'm sorting by thickness. And I can color it by the thickness on the screen. And so if I want all of those green shells to be 6mm instead of 5, I simply change one of them. The group properties are modified, and I don't have to click 7 or 8 other bodies and make that same change. So of course, the visual feedback makes it easier to make sure that you've set up the problem correctly, and this table interface is going to make it so that you can update this with a lot fewer clicks. So just to recap on SOLIDWORKS Simulation, we've got the new load case manager. We can view nonlinear results during the run, frequency response graphs, shell manager, and in general we're talking about fewer clicks and a more intuitive interface to sort of keep track of the setup for all of our stress analyses. Let's look very quickly at flow simulation. If you've used flow simulation before, it's our CFD tool. You may be aware that some of the goal plots that we've been able to set up in flow simulation can help you figure out if a particular version of a design is meeting the requirements that you have. So here I've got a globe valve, and in this case I probably want to examine the behavior of this particular valve at different settings, if it's fully open or partially closed, or 3/4 of the way closed, for example. And so now in flow simulation, I have some more powerful capabilities in the compare functionality, which lets me examine the results between those different versions. So in flow simulation, I have my nice compare menu. Let's say if I activate the first analysis, which is of the fully open valve. Previously, I would be limited to pretty much comparing either the visual plots, like the cut plot in this case, or the values of the goals. But we have a lot more capabilities now, so that if I, for example, want to load in my goal plots, let's go ahead and create this with all of the values of our goals. We can compare those values, but also we'll be able to show them in sort of a chart-like interface. And I can also compare XY plots now. And let's look at what that means very quickly here. So I'm comparing these three things across all the different flow projects that I've created. And without having to export anything to an Excel spreadsheet, I can click right over to these tabs. I can view cut plots like I've always been able to do. But now when I go to view and compare my goals, I'm presented again with the goal values like pressure drop across the different analyses. And I can view the numerical format like always, but now I can also view it in a table method. So here I'm looking at a line graph comparing the, in this case, velocity, inlet pressure, outlet pressure, etc. across the 4 different scenarios here. And I can also change it to bar graph, which might be a little more appropriate for this particular situation. So right away, I've been able to figure out that the scenario where the highest inlet pressure is occurring is when the valve is 1/4 of the way open, which makes sense. Can also compare XY plots. Here we're looking at an XY plot of velocity along the inlet channel of this valve. And of course, I can even zoom in and sort of compare the trends here. This is the overall length. I can look at also velocity just from the X component here. And I can zoom in using these magnification tools and figure out where the trends start to diverge. So again, much more capability to view and compare these plots between different studies without having to export anything to Excel or create the visual graphs later on. We also have some improvements to leak tracking. Leak tracking is a lot more colorful now. It will be easier to figure out where or if you have gaps in the model. And another enhancement to flow is that if you're running a flow simulation project, you can now also prepare or edit an existing CFD project in another configuration of your model while the first one is running. Previously, you were limited to that, where if you were running the flow simulation project, the SOLIDWORKS interface is sort of locked up, and you would not be able to create or edit another flow project at the same time. Now you can, so it behaves the same way as stress analysis. Okay, let's wrap up here by talking about SOLIDWORKS Plastics. Again, SOLIDWORKS Plastics is the injection molding simulation tool inside SOLIDWORKS. So some of the enhancements for SOLIDWORKS Plastics in 2015 are related to getting results that are just as accurate in a lot less time. And so one aspect of that is the new ability to account for symmetry in any of your models. If we have a part, for example here, this is the slot center from that previous CAP example that I showed you, where we were running the nonlinear analysis. If I turn on my plastics add-in, I would be able to run a plastics analysis on just this one part and figure out, for example, how long it would take or how much pressure from the injection machine it would take just to fill this one part. But we know that in the real world, that I probably would have a multi-cavity mold where I'd be trying to make about 5 or 6 or however many of these things all at the same time. So to do that, of course, I would need to analyze the full mold layout, which I have modeled here in this other configuration. But of course, since that full mold layout with all the parts and all the runners is a lot more geometry, it would take more time to run that simulation compared to just the one part. However, in 2015 now, we can take advantage of the symmetry in this layout and get the results for the full mold without actually having to run and analyze all of this geometry. So here, back with just a single part, I can go and generate my mesh like we normally would do. Here I've specified the runner already. I'm setting a circular runner here with a 10 millimeter diameter. And then when it comes time to generate the solid mesh, here's our existing surface mesh. I can select my symmetry options here, and I can pick either a half symmetry, I can pick quarter symmetry, or I can even pick circular symmetry and just choose how many items I want in that pattern. So 5, 6, etc. And of course, as I mentioned, I'll only be able to, or I'll only have to run the analysis on one of those items, but I'll get the results that would match the full model layout. So here, of course, I can go look at the results that I already had run earlier. In this case, for example, I'm showing a fill time of about 1.3 seconds, and I'm showing pressures of about 55 MPa in this case that are certainly higher than if I was only analyzing one of the parts. And of course, that matches the real-world increase in pressure that I would need to make 5 of these all at once. Another result enhancement we have in plastics is called a venting pressure. This now is able to show us that if we have potential air traps in our cavity, what the pressure of that air might exceed or be elevated to from the injection molding process. Previously, we could only see where air traps would be located, which would sort of give us a general idea of where we would add vents. But now we can actually see what the air pressure would be if it gets trapped by the injection process, so that we'll have an idea if it will really be a problem or if we can kind of ignore it. So here, this is showing us that we've had these air traps in some of the corners of this slot center, and the pressure, the air pressure, would be getting up to pretty high levels, 9 MPa in some spots. So to correspond with that, we can now also add or define air vents in our simulation so that we can get an idea of whether or not adding vents to the mold will really help. If it will really make a difference in lowering that air pressure and preventing, for example, burn marks or any other undesirable effects. So here, for example, some air vents have been defined at those exact locations where I had the high pressure spots. And after I ran this analysis here, again, this would take about 4 or 5 minutes on this particular model, I can go back to that venting pressure plot and notice that the pressures are vastly reduced. The highest pressure, in fact, is below 1 MPa now, and so almost a 90% reduction. So hopefully that's some more useful info to help figure out how the mold should be designed in various cases. Finally, the last thing in plastics that's been added to help get you results a little bit faster is a new meshing technology. If you're familiar with the solid mesh capabilities we have in plastics, which are needed to analyze any kind of parts that have either a significant internal volume or just don't really have constant wall thicknesses, we've always been able to do 2 kinds of solid mesh. We call them tetrahedral and hexahedral. So the process is always, for example, in this case, generating the triangles around the exterior of the cavity, which is what I'm going to do right here. And then the next step would be to fill in the solid mesh from there. That's how the traditional tetrahedral mesh was always generated. Sometimes, however, parts like this one with a lot of surface area but not as much internal volume can take a long time to run with this kind of a solid mesh. So the hexahedral mesh is a different approach where it sort of splits up the entire volume of the part, more like the mesh in SOLIDWORKS flow simulation, where each mesh element, or cell as we call it, is sort of rectangular in shape. So that's called the voxel mesh, and in previous versions of SOLIDWORKS plastics it would look like this, basically being able to mesh the part with fewer elements, but not particularly matching the geometry very well in some areas, especially where you have lots of curvature. So new for 2015, we now have what's called the non-orthogonal voxel, which is the same general approach of creating that XYZ grid to mesh the part, except now at the surfaces of your component where you have these curved faces, the cells will be trimmed accordingly, and it'll give you much more of a realistic representation of that true shape of the geometry, not just treating it as sort of a 3D voxelated mesh that does not really match the true borders or outline of the part. So now the non-orthogonal voxel can mesh the part in the same number of elements with much better accuracy, and it might end up being a better solution than the solid tetrahedral mesh that we were using before in a lot of these scenarios. That, of course, is something you can try out on your own models when you decide to run plastics in 2015. The results will be the same no matter which meshing technology you use, but each one will be faster in different scenarios. So go ahead and play with that, and it's now another option, another capability for you to try. So again, we can now do symmetry in our mold cavities to speed up on multi-cavity analyses, real-world molds. We can do venting analysis in plastics to figure out ideal vent location, or if it's even required in the first place. We have some meshing improvements, like the non-orthogonal voxel mesher, and we also have a new thickness advisor to evaluate where exactly wall thicknesses have been changing, and if we're trying to optimize the design of a part, what we should focus on first. So that sums it up. Those are the main enhancements in SOLIDWORKS Simulation 2015. If you haven't installed it already, we're now currently at SOLIDWORKS 2015 Service Pack 1.1. So we're recommending all of our customers upgrade and just do the installation, which you can go to from help and then check for updates inside your SolidWorks user interface. If you have any questions, please send an email to support@awkwardssys.com. If you have technical questions, contact your account manager. Of course, everything you need can be found on our website, including phone number. Thanks again for attending. If you have any follow-up questions, I will be hanging on to the webinar here to see if I can answer them for you. Otherwise, if you don't have any other questions, have a good rest of the day. Thanks for attending.